Okay, for our 10.1 day 2 notes, we are going to continue the problems we were working on yesterday, starting at number 7. And number 7, we're given the circle here where our angle at center O is 1.4 radians. And we are told that the radius of circle O is 6 centimeters. And the problem is asking us to find the shaded area right here. So what I'm going to recognize is we know how to find the area of this sector, and we also know how to find the area of this triangle. And if we subtract those two areas, we should get the area of the shaded region that we're looking for. So the first thing that I'm going to look for is my area of the sector. And remember that that formula is 1/2 radius squared times theta. Remember that theta must be in radians. We have that, so we are all set to go. So if I plug in my values, and I round this to 1 decimal place, I get that the sector is 25.2 centimeters squared. Now let's go through and find the area of my triangle. And remember that new formula we learned yesterday was 1/2 times the two sides times the sine of my angle. And this triangle is side angle side, so we are all set to go. And so when I plug that into my calculator, this one I will round to 2 decimal places. We get 17.74 centimeters squared. So then, like we've already said, now we just need to subtract these two areas for our final answer. So I'm going to take that sector area, because it's larger, and subtract the area of my triangle. And so when I do that, I end up getting that my shaded region is approximately 7.46 centimeters squared. Moving on to problem 8 now. So for this one, we are told that from a point on the ground, I measure the angle of elevation to the top of a mountain to be 38 degrees. So over on the side here, I'm going to draw this in. So my mountain is over here. And I am standing over at this point. And I know that that angle of elevation was 38 degrees. Then what I'm going to end up doing is I'm going to walk 200 meters farther. So I'm going to walk this way. So this is an additional 200 meters. And now at this angle, I know I have an angle of elevation of 20 degrees. And so what we're doing is we need to find the height of the mountain. So I'm going to label this as X. Now, given that this 200 is over on the bottom side of my diagram here, what I'm going to end up setting up is this segment here is going to be Y. And so now when I'm looking at this blue triangle, if you notice we have an opposite and an adjacent, since this angle here should be a right angle. And so I'm going to set up tangent of 38 degrees is going to be X over Y. And then if I'm thinking of my red triangle, well, my opposite is still going to be that same value X, but now my adjacent value should be y plus 200. So I'm going to set up then tan of 20 degrees is x over 200 plus y. If you notice now, we have a system of equations. We need to use this system in order to find the value of x, which would give us the height of the mountain. Okay, so let's go ahead and do that. What I'm going to end up doing then is this first equation that we wrote, I'm going to go ahead and solve for y. So I end up getting that y times tan of 38 degrees is equal to x. And so I know that y is equal to x over the tangent of 38. Now I can take this value and I can substitute it in for the y in my second equation. So let's go ahead and do that now. I get that tan of 20 degrees is x over 200 plus that first equation. And so now stay with me for this algebra when I go through and simplify this, because we do need to solve for x. So the first thing that I'm going to do just on the right-hand side here, I'm going to multiply both top and bottom by the tangent of 38. And so when I do that, I'm going to end up getting tan of 20 degrees equals x tan 38 over 200 tan 38 plus x. Now I'm going to go ahead and I'm going to get rid of the fraction. So if I do that, I'm going to cross multiply both sides and also distribute at the same time. So I'm going to have tan of 20 times all of this in the bottom. So I end up getting 200 . So we get up 200 tan 38 tan of 20 plus x times tan of 20 equals x tan of 38. Okay, here I want you guys to recognize we have two terms that both have the variable that we're trying to solve for. Since these terms both have a variable, we're going to move them to the same side. And the reason we're going to do that is so then I notice that I can factor out an x term from both of these, and so we can more easily solve for our variable. So I am going to go ahead and do that. If I factor out the x here, so I know everything on the left should be the same. And then if my final step, I'm solving for x, remember, so I'm going to divide both sides by this tan of 38 minus tan of 20 degrees. What you can do now is plug this entire left side into your calculator. And when you do that, you should get that x is approximately 136 meters, because remember the problem originally asked us to round to the nearest meter. Moving on to problem 9, we now have this diagram where we have an arc that is part of the unit circle and where theta is in degrees. So the first thing that we're going to do for part A is find all of these angle measures in terms of theta. So if I'm looking at angle BOA here, I have angle BOA here. Well, I notice that angle BOA and theta both make up my right angle. And remember, since we're in degrees, we can then go ahead and say that this angle should be 90 minus theta. Okay, well, so if this guy over here is 90 minus theta, and we notice that these two angles at vertex B are both right angles. Then when the next problem is asking for the measure of angle OAB, well, angle OAB and the angle we just found, BOA, they should add up to 90 degrees. So we know that this angle now should be theta. Okay, so let's go ahead and label that in as well. Next angle we're looking for is angle BAP. So angle BAP is this guy over here. And again, this angle plus the angle that we just found, angle OAB, should add up to 90 degrees. And so if that one angle is theta, then the second one should be 90 minus theta. And we'll go ahead and label that one as well. Okay, and then finally the last angle that we're looking for, BPA, that is this angle right here. And then same kind of reasoning. We noticed, okay, in this triangle, I already have a right angle. I already have 90 minus theta. So this last angle should also be theta. So I have all of part A labeled and solved for in terms of theta. For part B now, what we are asked is to find the following lengths in terms of sine theta and cosine theta. So the first thing that I want to do is I'm going to highlight the first side that we're looking for. And because I'm looking for either sine theta or cosine theta to use to represent this length, I'm going to recognize that my angle at P, because it is because it is theta, I am going to highlight this whole triangle AOP, and it should help me get AO in terms of either sine or cosine. And so really quickly off to the side, what I'm going to do, I'm going to redraw this triangle. And so remember we have a right angle at A, and we know our angle P was theta. Last piece of missing information, remember that this arc is on our unit circle. Because our arc is on the unit circle, I can call side OP a length of 1. Now that I know that that has a length of 1, if I'm looking for AO, well, I can simply set up that sine of theta is equal to my opposite, AO, over the hypotenuse, OP, which I know to be just 1. So I know already that AO is just simply sine theta. Okay, well, for AP, I can use the same triangle because now AP is the adjacent. So instead of sine, I'm going to say cosine of theta equals AP over my hypotenuse of 1. And so I know AP is just simply cosine of theta. Okay, since we know that, when I go through and find OB and BP, what's going to be helpful is if I label these two sides that I've already found in my diagram. So again, we are looking for side OB now, so I'm going to highlight him. And I am looking for a triangle that has theta and this side. So I'm going to now highlight triangle AOB. And again, just to make it easier to visualize, let's go ahead and redraw him off of our given diagram. So we have our right angle at B and theta is at angle A. Remember that OA we already found to be sine theta. Okay, so when I am looking for side OB now, I notice that's the opposite of this angle theta, and I am given the hypotenuse. We found that to be sine theta. So now sine of this angle A should be equal to side OB over side OA, which we found to be sine theta. And if I simplify that a little bit, I get that OB should be sine squared theta. Okay, well then last piece of information that we're missing is looking for BP. Now I'm looking for this side. And I notice, okay, my angle theta has angle P in the triangle. So we are going to use triangle APB. And again, I will draw it off to the side for you to visualize. We have our right angle at B, and P was my angle theta. We also already found that side AP is cosine theta. So now if I'm looking for side BP, well, that's the adjacent of my current angle P. So I can set up cosine theta equals my adjacent side BP over the hypotenuse AP, which we already found to be cosine theta. And so BP should equal cosine squared theta. Problem 10, we are given this diagram and we are told that AB is 8 inches. So I will go ahead and just label that. And we are told to express x as a function of theta. Now, one of the first things that I would like to do is I would like to extend this segment here and create a larger triangle. And what I want you guys to remember from geometry is if we have two lines that are perpendicular to the same line, then those lines are parallel. So I know that this line here and this line here are parallel. Okay, well, if those are parallel and line AB is my transversal, if angle B is theta, then this angle in this other triangle with a vertex of P should also be theta. Okay, so then moving on from here, what I'm going to notice is that since it gave me side AB was 8 inches, and on both of these smaller triangles, that makes up part of the hypotenuse for both of these triangles. For this first triangle up here, I will highlight him in blue and call him my blue triangle. So for this guy, since I am going to be looking for representing side AP, I'm going to set up that since I have the adjacent and I'm looking for the hypotenuse, I'm going to set up cosine of theta equals x over AP. And then I'm going to simplify this a little bit. So I'm going to put cosine over 1 and cross multiply. So I know that AP times cosine of theta should be x. And then if I divide by cosine, AP is x over cosine theta. And knowing my trig properties, I can rewrite this as AP is x times secant theta. Okay, now that we're done with this blue triangle, let's go ahead and work with this other triangle. We'll call him our red triangle. And so now in my red triangle, kind of similar to what we did in blue, I'm specifically looking to get BP in terms of theta. So the given side is my opposite side. So now instead of cosine, let's go ahead and use sine of theta is equal to 4 over that missing side BP. Do the same manipulation as we did with our blue side. So BP times sine of theta equals 4. BP is equal to 4 over sine theta. And again, with our trig identities, BP should be 4 cosecant of theta. Now, why did we manipulate this as such? The reason I did that is because remember that these two things, these two sides, added up to 8. So if I know that that adds up to 8, what I can do is I can say x secant theta plus 4 cosecant theta equals 8. And since I'm solving for x, well, let's go ahead and do that algebraically. So I know that x, I lost my x here. X should be 8 minus 4 cosecant theta over secant theta. And you can leave your answer as that. For 11, we are given this diagram of the Earth and the Moon. And we are told that r is the radius of the moon. You should also know that PT is tangent to my circle, to my moon. So we know we have a right angle there. And I know it's kind of small, but we do have theta over in angle P. And so for part A, we are trying to show that r equals sine of theta over 1 minus sine theta times the length PS. Okay, so what are we going to do here? Well, since we know that we have this right angle, what we can do is we can say, well, this is my radius r, and this is also my radius r. And since my answer has PS, well, I might have to think about the length of PM being PS plus my radius r. Okay, so knowing that now, well, based off of theta, I have a opposite side and I have a hypotenuse side. So let's go ahead and set up sine of theta is equal to r over PS plus r. Okay, from here, what we're going to have to do is manipulate this equation to get r by itself, and hopefully it will look like the right-hand side that we are given. So I'm going to go ahead and multiply both sides by PS plus r. And so when I do that, I'm going to distribute at the same time on my left-hand side. So I have PS sine theta plus r sine theta equals just r. Now from here, like a few problems we did a while ago, I have one term with an r and a second term with an r. Get all of those r terms on one side so that we can end up factoring r out. And so what that looks like now, we have PS times sine theta equals r minus r sine theta. And if I factor r out, and then solve for r, so divide both sides by 1 minus sine theta, we end up getting that r is equal to sine theta over 1 minus sine theta. And that whole thing is multiplied by side PS. Now, for part B, it's telling me, well, what if the length of PS was this big number and my theta was this very small angle? What should r be to the nearest 10 miles? Well, this should be pretty simple because we already know that r is equal to this equation that we solved in part A, that we proved in part A. So let's plug in the values that we know. R is sine of my angle divided by 1 minus the sine of the angle. And we are going to multiply this whole thing by the side PS. And when I plug that into my calculator and round it to the nearest 10 miles, so we're going to round it to the 10th place, we get that we should have about 1,080 miles. for the radius of the moon. Our last problem that we're going to be looking at for 10.1 is asking us to find the area of a lune. Now, the area of the lune is going to be this part. I know it doesn't look like a semicircle, but we are assuming that these are semicircles, minus that shaded in part between points A and B. So we are looking for this area, and all of these steps are going to walk us through finding the area of the lune. So for part A, it's saying that given circle O is a unit circle. So remember, our unit circles have a radius of 1. So I'm going to go ahead and label our radii of 1. And we are looking for the measure of an angle, of a specific angle AOB in radians. Well, if I'm looking at my figure, I do have a hexagon here. And if I have a hexagon, I can really split it up into 6 different triangles. And so for those triangles, if I have 6 of them, then I know that this guy should be 60 degrees, simply because I do 360 divided by the 6 triangles, and we got 60 for each. Okay, but part A is asking for 60 degrees in radians. So remember, on our unit circle, that would be the angle pi over 3 in radians. Part B is now asking us to find the area of the hexagon. So we are going to go back on the idea that there's 6 congruent triangles in this hexagon. Remember that I can find the area of any triangle by using that formula 1/2 AB sine theta. Because in our diagram, I know my 2 sides are both 1, and my theta is pi over 3. Well, sine of pi over 3 is square root of 3 over 2. So the area of one triangle is the square root of 3 over 4. Since I'm looking for the area of the hexagon now, I know 6 triangles with an area of square root 3 over 4. The area of my hexagon should be square root 3 over 2. Okay. So now in part C, we are to find the area of this shaded segment. Now, the shaded segment is the difference between the sector of the circle, so sector between AOB, and the area of that one triangle AOB. So the first thing that I'm going to do is find the area of the sector. And remember that that formula is going to be 1/2 r squared theta, where theta is in radians. So that sector should simply have an area of pi over 6. So the area of the shaded is going to be congruent to the area of the sector, pi over 6, minus the area of the triangle, square root 3 over 4. And so if I combine this into one big fraction, common denominator of 12, so I get 2 pi over 12 minus 3 root 3 over 12. My final answer should be 2 pi minus 3 root 3 all over 12. For part D, it's now asking us to find the area of semicircle ACD. B. Now, going back up to our diagram, we've already talked about how there's 6 different triangles within this hexagon. Remember that all 6 of these triangles end up being equilateral triangles. They end up being equilateral and equal angular. And so length of AB should also have a length of 1. Since AB has a length of 1, and we are told that ACB is a semicircle, then I should know from that information the radius of my circle, of my semicircle, is going to be 1/2. So when we go back down to D, if I'm recalling the area of a circle, well, that's just pi r squared. So the area of my semicircle should be 1/2 pi r squared. And we just talked about how that r, how my radius is going to be 1/2. And so when I simplify this, I end up getting that the area of my semicircle is pi over 8. So then when we move on to part E, this is what we've all been waiting for, finding the area of Lune ACB. I've already talked about it at the beginning of this problem. That area is going to be the area of the semicircle minus the area of that shaded region. And lucky for us, we have found both of these areas. So that should be pi over 8 minus the area of our shaded, which was 2 pi minus 3 root 3 all over 12. So now I would like us to go through and simplify this a little bit. So the first thing I'm going to do is get rid of this negative. I'm going to change it into plus a negative 2 pi plus 3 root 3. And then between 8 and 12, I can get a common denominator of 24. So we should get 3 pi over 24 plus negative 4 pi plus 6 root 3 over 24. And then the last thing to simplify there will be that 3 pi plus that negative 4 pi is going to be negative pi plus 6 root 3 all over 24. And that is our area of our lune. For part F here, we're going to show that the area of this hexagon is equivalent to 6 times the areas of the lune plus 2 times the area of our semicircle. Okay, well, good thing we have all of these areas already. So it's asking us for 6 times our lune area. And remember, our lune area we just found to be negative pi plus 6 root 3 over 24. Plus 2 times our semicircle area, and that we found to be pi over 8. And if I go through and simplify, the 6 and 24 will simplify, so I just have 4 in my denominator. And again, the 2 and the 8 will simplify, so I just have 4 in the denominator. So I have negative pi plus 6 square root 3 over 4 plus pi over 4. From here, the negative pi plus pi are going to cancel out. So we are left with 6 root 3 over 4, which is equal to 3 root 3 over 2. And yes, that is the area of the hexagon that we ended up finding in part